This video is going to cover section 2.2, complements, subset, and Venn diagrams. Okay, so we're going to go ahead and start with the definition right off the bat. This is called the universal set, denoted with U. And this is the set of all the elements that are being considered when we're talking about complements. Okay, another definition we have is the definition of the complement. So the complement of a set A, whatever letter you want to use, is denoted by A prime. So that little apostrophe there, we say prime. So this would be A prime, okay? And pretty much A prime is the set of all elements that are in this set, in the universal set, that are not in A. So if it's not in A, it's in the other one, in A prime, okay? So we're going to start right with an example just to kind of show you this idea. So we're going to let U, the universal set, so the set that where all the elements are being considered, be equal to 1, 2, 3, 4, 5, 6, 7, 8. So pretty much 1 through 8. H is equal to 2, 4, 6, 8, and T is equal to 1, 3, 5, 7. So we have these three different sets. The universal set, which again is this one, okay? We have H and we have T, which are just other sets that, happen to have less numbers in these. So we're first looking for H prime. So let's first write what that means. This means all elements, okay, that are not in H, okay, so kind of like over here, but are in U. So all we're going to really look at is U and H for this first one. So it's all elements that are not in H, but they are in U, the universal set. So let's go ahead and take a look at that. So H has a 2, 4, 6, 8. So U also has 2, 4, 6, 8. So I'm looking at the other one. So it has a 1. So I would say that H prime has the set 1. It has 3. It has 5. And it has 7. And that's it. So H prime is equal to this, the set with 1, 3, 5, and 7, because 1, 3, 5, and 7 are not part of the original H over here, okay? We're going to look at another example. So now we're looking at T prime. So now we're looking at this one over here, so the set T. And T prime means all elements, just like the first one, okay? All elements that are not, I gotta write this a little bit nicer, that are not in T, okay, but are in U, the universal set. So I'm going to do the same thing. Here I have 1, 3, 5, 7. So over here I have 1, 3, 5, 7, but I don't have 2. I don't have 4. I don't have 6. And I don't have 8. So T prime is equal to 2, 4, 6, 8. The set of that. Okay. And that's it. So complement is pretty much whatever is not in that set, but it is in the universal. Okay, so what's usually going to happen is your universal set will be defined. So in this case, our universal set was all this, and then you'll be given the other set, and they'll say what's not in here that is in here. Okay, that's it. So let's go ahead and move on to another example. It's a little more complicated. Okay, here we have that U is equal to all of this now. So this is the set that is our universal set. Okay, this is our universal sets. M is equal to 0, 4, 6, 17, and P is equal to this craziness. So P is equal to X such that X is less than 7 and X is an element. Sorry, that got erased. of the even natural numbers. So let's just really quickly remind ourselves what that is. The natural numbers, remember it's with that n, are equal to 1, 2, 3, okay? But this is saying the even ones only, so that means that I don't really want all of them. I just want the even ones. So 2, 4, 6, and so forth, okay? Now, this is saying that its x is less than 7, so we have to have this condition and this condition. So going back to the list that I made over here, I'm going to have to consider anything that's less than 7. So I'm going to erase that 8 because 8 is not less than 7. So essentially what I'm looking at is only these three numbers, 2, 4, 6. Okay, so this right here represents the set P. And that's a lot easier to look at than all this craziness right here. But it does take a little, you do have to be able to apply this to this. Okay, let's go ahead and look at the problems now. The first one is asking us to find m prime. So remember, I'm not going to write this out. I'm just going to kind of say it. But m prime is all the elements that are not in M, but they are in the universal set. So we're going to look at M. Okay, let me get a different color actually. We're going to look at M, and I have a 0, 4, 6, 17. So over here, see 0, 4, 6, and 17. So those numbers I can't use because they are part of M. So what I have left over for M prime is a 2. Don't forget that curly brace. I have a 3. I have let's see what else, a 7, and that's it. I can't use anything else because the other numbers that are in here are also in M. So I only want the ones that are not in M. So that's my answer for that one. Let's go ahead and look at P now. So we're looking at P prime, which again, remember that P prime is all the elements that are not in P, but they are in the universal set. So they are going to be in U. So remember, P is over here, 2, 4, 6. So anything that's not equal to this, I can include in the set. So P prime is going to be equal to, let's see, I can't use 2, I can't use 4, and I can't use 6. But I do have a 0, I have a 3, I have a 7, and I have a 17. So this would be my answer for P complement. Okay. I was saying prime earlier. Go ahead and you can use the word complement. That'd probably be the better word to use here. So go ahead and up here, you can use the word prime, but I'm going to go ahead and put complements because we are talking about complements in this one. So you might want to use this one instead, just for this lesson. Okay. All right. Going too fast. So yeah, that's pretty much it for how to use complements. And of course, they can get more complicated. I'm sure you could guess that with this kind of notation here, it can get a little crazy. So just be careful and read carefully, okay? I have a special note here. I just want you to take note of it, that the complement of the universal set is the empty set. So remember that the empty set, in case you forgot, it's this weird like zero looking thing with a line going through it, slanted, okay? This tells us that the complement of the universal set is the empty set, and the complement of the empty set is the universal set. So what that looks like, let's say we have U, okay? The complement of U would be U complements, okay? So U complement is going to be equal to that empty set, okay? And the complement of the empty set, so the complement of this empty set complement, okay, is going to be equal to the universal set. And it's just something you want to take note of because it's one of those properties you just got to know, okay? Although it would be interesting to see how we prove this. I'd be interested if anybody tried that, okay? We're going to go ahead and move on to the next topic of this section, okay? We have a new definition here. So we talked about complements. We're going to talk about something called a subset, okay? Set A is a subset of set B, okay, denoted by A subset of B. So this is the notation for subset. Pretty much that weird looking C thing right there, C with the line. If and only if every element of A is also an element of B. Okay. So in other words, if all the objects that are in A are also in B, then A is going to be a subset of B. Okay. We have two special notes here, so do take note of them. We have that A is a subset of itself for any set A, which means that if all the elements are in A, then all the elements are still in A, so it's still a subset of itself, okay? And the empty set is a subset of A. That one I'm not going to go too much into. For a few extra points, maybe you could elaborate on that for me, okay? But it's true. We also have to note that not a subset. So if A is not a subset of B, this is the notation for that. It's like the little C you have here, but with the line going through it. So that means not a subset. Okay. So we're going to go right into some examples just to see how this is used. Let's look at letter A. We have that, by the way, we're determining just true or false. Okay. So we have 1, 3, and 5. So let's say that this is A and this one is B. Okay. We want to know if A is a subset of B. So let's see. A has a 1 and B has a 1. A has a 3, B does not have a 3. Does not have a 3. So right away, this would be false. Or you could also say that A is not a subset of B using the notation we have here. Okay. Next one. Let's call this A. Let's call the other one B, like we did before. Okay. A has, let's see, A is three elements, -6, 0, and 11. And then B is the set of integers. So just really quickly, in case you forgot, remember the integers are equal to dot, 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 -3, -2, -1, 0, 1, 2, 3, and it goes on and on. The integers are pretty much all the whole numbers, including the negative ones and 0. Okay, so in other words, all these numbers are part of set B. So -6 would be in there. 0 is here, it's right in the middle, and 11 would be somewhere over here. So all of these are in fact inside the set of integers. So for this one, we would say that it's true, that A is in fact a subset of B. Okay, and finally, not finally, we have two more. So almost finally, the set of counting numbers is a subset of the natural numbers. So for this one, you kind of have to go back to the section we did before, section 2.1, and we did in fact note that the counting numbers, so this one is the same as the natural numbers. So these are the same. So that means that we're going to use this definition right here. Let me kind of highlight it a bit. This definition right here, where one set is a subset of itself. Okay, so in this case, this would be true. This would be kind of like your A. This would also be A because they're the same exact thing. So A is a subset of itself. Yes, true. And finally, the last example for this little part right here, we have this weird thing is a subset of U. So let's define what this is. This right here is the empty set. Okay, and U is the universal set. So how could we define this one? Well, remember that according to those little notes that I put up here, okay, it says that the empty set is a subset of A for any set A. So what do you think that means? I'm going to give you a few seconds to think about that and see if you can answer this problem. So take a few seconds. Okay, So what do you think? If it's in the definition, okay, then by definition, it should be true because it tells us that the empty set is a subset of every subset. So this one would be true. Okay. I think that's it on this side. So we just have one more thing to cover, and then we will be done with these notes. Let me see. Here we go. All right, so last definition for section 2.2. We have that set A is a proper subset of set B. So proper subset is the new definition here, denoted by a proper subset of B. So it's kind of like the one before, but it doesn't have the line, the equal to, okay? If every element of A is an element of B, so everything in here is also in here, and A is not equal to B. So this is the important thing here. One way to think about this, I guess you could say that they're not on equal terms just because if one of them has all the other ones, if they're equal to, then they would just be, on the same level. And we don't want a proper subset, kind of like a proper subject. Think of a kingdom is not equal to its superior. So think of it that way. Okay. So let's look at the first example and see if we can apply this definition to that. So it says determine whether the first set is a proper subset of the second set. So let's call this set A and let's call this one set B. Okay, so in set A, we have an A. So yes, we have an A over here. Yes, we have an E. We have an E. We have an I. We have an I. We have an O. We have an O. We have a U. We have a U. So it looks like all of the set A. So A is in fact a subset of B, which is what we covered on the other side. Okay, but it also looks like they're equal to because all the elements in here are the exact same as over here. So A is also equal to B, which means this implies that this is not a proper subset because one of the conditions says that A cannot equal to B. So the moral of this story, yes, A is a subset. So A is a subset. Okay, so it is a subset, but it's just not a proper subset. So it's a different type of subset. Okay, and why? Because of this part right here, this little part right here. Let's look at one more example, and then we'll be done. The set of natural numbers and the set of integers. So just again as a reminder, the natural numbers are the numbers that start with 1 and it goes whole numbers up from there. 1, 2, 3, 4, etc. Okay, and the set of integers. So the integers are the I. So the set of integers is going to be dot, 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 -3, -2, -1, 0, 1, 2, 3, and so forth. So this is saying that this one is a, we want to know if it's a proper subset of this one. So what do we think? Well, if we look at the numbers 1, 2, 3, 4, we also see them over here 1, 2, 3, and then they go on forever. So we for sure, n is a subset of the integers. So subset, yes, okay? We want to see if it's a proper subset. So for a proper subset, remember we have to have this condition not be true. So A cannot equal to B. So is the natural numbers equal to the integers? That's the question we need to answer. Well, it looks like the integers have all these other numbers over here as well, and the natural numbers do not include the negatives. So n is not equal to I, which means that according to the definition we have up here, if this is not equal to and every element of A is an element of B, so in other words, if it's a subset, which was true for us, then this in fact is a proper subset. So this means that yes, n, which is the natural numbers, is a proper subset of I. And that is it for this section.